Hello and welcome back. I hope that you guys had a good weekend and enjoyed your time off. It was probably the first Easter where there was no one at church. That was pretty weird, but I hope you guys enjoyed your time off. So we're going to continue on. We're going to finish up this chapter this week. So we're talking about confidence intervals and hypothesis testing with inferences with means. Today we're going to talk about choosing a sample size. So it's the same process we use with populations or with proportions, but now it's applying to means. So instead of using the standard normal model, now we're using Gosset's family of models or students models here. So just a small step is going to be a little bit different. So we're going to be going through example on page 579 in your book. So if you want to look at that, we're going to go through that today. It'll be really short. I've only got 7 slides today, so I'm going to try to keep it pretty short. But we're going to go through each one of the processes that we might want to do with this one sample. So in 2004, a team of researchers published a study of contaminants found in farmed salmon. Fish from many sources were analyzed for 14 organic contaminants. One study expressed concerns about the level of contaminants that were found. One of those was the insecticide Mirex, so a chemical that they were using to maybe control algae populations in the salmon farms. They were afraid that this carcinogen Mirex was getting into the salmon and could be consumed by the humans eating this farmed salmon. So it's been known to cause cancer and is suspected to be toxic to the liver, kidneys, and endocrine system, which I believe controls your hormones. One farm in particular produced salmon with very high levels of Mirex. After those outliers were removed, the summaries of the Mirex concentrations in parts per million ppm and the rest of the farm salmon are as follow. Then they give us the summary statistics for that. Let me click over here. There we go. All right, so our assumptions and conditions. So they sampled 150 salmon from 51 different farms. So is this a random sample? Well, we are randomly sampling from all these different farms, so it should be a random sample, which means it should be representative of all the salmon that is being produced in that region or the salmon that you would find in the market. So that should be good. The next question is each sample independent from the next sample? Well, if you think about it, each salmon is living in the same pond or the same farm. So if one salmon has high levels, it's in the same environment as the next one. So those in the same farm are probably going to be related to each other, and so they're not independent. But because we're sampling from all the different farms and it's a random sample, that should guarantee that we have some level of independence. Also, when we sample one fish and we take a sample from it, we're not replacing it where we could sample it again. So we're not sampling with replacement. And anytime we sample without replacement, it's not truly going to be independent. So we can override that with the 10% condition. So the independents were bought from several farms, from several different sources. So if we were only sampling from one farm, of course, we could not say that was a random sample, nor would it be representative or independent, because they're all going to be related to each other because they're all living in the same environment, being surrounded by that chemical Mirex, the insecticide. So 10% condition, we are sampling 150 salmon is way less than 10% of the population. So even though we're sampling without replacement, it's less than 10% of all farm salmon, so we're good with that. Nearly normal. So what we need to do, what we are concerned with when we're talking about means instead of when we're doing proportions, is do we believe that the population it came from was normal? Or is the sample size large enough that even though it wasn't unimodal and symmetric, the population is skewed like the CEO data, is our sample size large enough that our sampling distribution model would still be normal? So keep in mind, this is just a sample which is representing the population, and it looks unimodal, roughly symmetric. Maybe it's a little bit skewed to the right, but since we have a large enough sample of 150, even if this was severely skewed or bimodal or even unimodal or multimodal or something like that, with such a large sample, the central limit theorem is going to kick in and allow us to continue to use our inferential statistics like we want to anyway. So is our population, do we believe it to be nearly normal by looking at the sample? Yes. So after the outliers were removed, this looks like it's totally fine. We believe the population was normally distributed. are at our confidence intervals. So the first thing we might want to do is we get our sample statistics. So the average ppm particles per million was about 0.009 with a standard deviation of about 5% or 0.005 parts per million. Sample size was 150, which means the degrees of freedom is one less than that, is 149. Now that's important because we're referencing our T distributions or our T models here, and the T star, which is the critical value we need, is going to be about 1.76. Now typically if we were doing a 95% confidence interval, we would use 1.96, but now we're using 1.76. Now the reason for that is because we have we have a different family of models. This is an entire family of models from Gosset's distributions, and the normal model is going to be when our sample size is infinite. Now, with such a large, when we did have a normal model, to do 95% confidence, we use 1.96. But now we have to go a little bit further out because we're correcting for the fact that we're sampling means, where we're using the standard deviation of the sample, which is calculated from the average from the sample, not the actual population average, because we don't know what the population average is. And since the samples are always going to vary less from their own mean than from the population's mean, which is from what we discussed previously, we have to correct that by using a flatter and a wider normal model instead of the actual bell curve, the standard bell curve. So we didn't have to go that much further out, just a little bit further out. That's because our sample size was so large. When we have such a large sample, it does start to approach the normal model, so we don't really have that much of an issue, but we still need to correct for it because we know how to do it. So these values are found from the inverse normal. And so if you wanted to find what that critical value was, we would just go second distribution, and then we go down to not the inverse normal, because we're not using a normal model, but the inverse T model. The area under the curve we want is going to be, because we can't do it from the center, we're going to do, so if it's 95%, there's 2% or 2.5% on each side. So I'm going to do 2.5, and this will be just the critical value for the left tail, which is totally fine. I could do 97. It would give me the exact same value, 97.5. Degrees of freedom is going to be 149, and then we hit paste. And that's going to give us that value. Now, if we use the normal model, I guess I'll go ahead and show that. So distribution, So inverse normal, and if we wanted 0.95, or actually I'll do it from the left so you can see how it was the same thing. Standard normal from the left, which normally do the center, but we didn't have that option, would give us the 1.96. So notice it is only slightly larger, and again, that's because we're sampling with means instead of proportions, and we have to correct for the fact that the samples, their standard deviations, were calculated based on their own average, the sample average, instead of the population average. So there's more variation that needs to be accounted for. So we go a little bit wider. All right, so that's how we get the T star, which is the critical value based on our sample size, our degrees of freedom. Our standard error here is going to be the standard deviation from the sample divided by the square root of n, which would be 150, which gives us about 0.004 parts per million. Then to create our confidence interval, we just take our sample average plus or minus our critical value, which was found from technology, multiplied by the standard error, which is over here. And that'll give us confidence interval, looks like that, and there's our confidence interval. Now, how would we put this in the calculator to do that? We go to stat, arrow over to calculate, test. Now, we're not doing a test. This isn't a hypothesis test. This is an interval. It's not a z interval because remember the z is telling us it's a normal model, but instead we're going to do a t interval because we're using t distributions. So we don't have the data. Instead, we have the stats, the summary statistics. So I'm going to put my average in as 0.0913, so that's our sample average, and then the standard deviation from the sample is going to be 0.0495. Degrees of freedom, n in this case would be 150, degrees of freedom would be 149, confidence interval is 195%, and boom. So we get the exact same values. Again, our calculator will do all the work for you. All right, so that would be the first thing. So if we were interpreting that, we'd say we're 95% confident that the true average parts per million contamination I don't know, like the science stuff, but whatever, you get the idea. The Mirex contamination levels in parts per million is for the average for the salmon and the farm salmon that in the region that we gathered from is anywhere from 0.0834 and 0.0992 parts per million. All right, and that was with the outliers removed. Now, if we put the outliers back in there, then we would have more variation, and so our confidence interval would be much larger. So we do want to put an asterisk there, reminding them that we remove the outliers from that one farm that had a really high amount of Mirex in the salmon for the contamination. All right, Gosset's family models, we already talked about that. Moving on. The other thing we might want to do is a hypothesis test. So let's say that the FDA, Federal Drug Administration, determines that if you have an average, or if your average from your farm is more than 8% parts per million, 0.008, you get what I'm saying? If it's more than 8% parts per million, then they won't let you sell your salmon or something like that. So you would, our null hypothesis would be that you were in compliance. So this is the amount of Mirex that contamination you're allowed to have, and for it to be safe for human consumption or something like that. So our null hypothesis, which is the H naught, is that your farm has an average of 8% parts per million. The alternative is that it's going to be higher. And we're only interested in a one-tailed alternative because we only want to know if it's higher than that value, which would mean that we would reject the null that it was within compliance, and we would not allow you to sell your salmon in the market. All right, so do we have enough evidence to say that the mean, oh, that's not right. That's from a different one. So we want to know, do we have enough evidence to suggest that their average parts per million is larger than the 8% that's allowed by the FDA? So same standard error calculation as we did before, same sample size, same sample. We have to determine what alpha level, what level of false positives are we okay with. So we have to determine the burden of proof or the significance level. So our default is 5%. If we're dealing with candy or unimportant things, we can do 10%, allow 10% of the time to be wrong with a false positive. So where we detect that there's a change when there really wasn't. But this one, we're probably gonna be a little bit more critical because we don't want to shut them down. But even if we, especially for a false positive, but if we didn't, we also could keep it at 5%. Either one would be okay. So what we want to do now is to put this in for a test in our calculator. Another thing we could do is calculate the t-score, which is like a z-score. Now this isn't the t-star, it's a t-score. So how many standard deviations are we on the bell, or not the bell curve, but on the Gosset's model? So it's our observation by the hypothesis mean minus the hypothesized mean, which is 8%. So how much higher was our average than that, divided by the standard error. And we'll put that in the calculator, and the model is parameterized by the degrees of freedom. So it's a T sub 149 is going to be 2.825. So we're 2.825 standard deviations above the mean from our sampling distribution model. So our average for our fish was 9% essentially, which is going to be about 2.8, which is about right here. So that would be in the top 1%. But keep in mind, we can't use the normal model. It's close to a normal model, but we actually are going to be using a model that's flatter and looks something more along the lines of here that we see here. So we want to put this in our calculator. We'll do that real quick. So we're going to go to stat or over to test, and we're doing, let's see, it's not proportion. So we're doing a one sample, let me see. No, it's just a t-test. Yeah, we're just doing a t-test here. And we would use a z-test with means if we knew the population parameters, which we never do. So we're doing a t-test. All right, we're going to use the data. So our hypothesized mean is going to be 0.08. The average from our sample, which is 9.13% parts per million. Standard deviation, we already put that in. Sample size, we want to hypothesize that it is larger than that for our null hypothesis. And then we hit calculate, and this will give us the p-value. Remember, it's calculating the p-value based on our t-score and the actual individual model that we're using, which is with degrees of freedom of 149. So our p-value in this case is less than 1%, right? So this is more statistically significant than any reasonable alpha level. So even if we chose an alpha level of 1%, we would still be able to reject the null. So question I would ask is, what does the p-value mean? Well, p is probability, right? So this is the probability, but it's a conditional probability based on what what condition. So the p-value is based on the assumption that the null hypothesis is true. So if this was actually the average, if the average parts per million contamination was 8%, the probability of getting a sample of this size to have a mean, which was 2.8 standard deviations above the mean, which we have over here. I can't really show that very easily, but the probability of that occurring is less than 1%. So would we consider this statistically significant? Yes. So we'd have enough evidence to reject the null hypothesis in favor of the alternative, which suggests that the average parts per million contamination is above the allowed FDA approved 8% parts per million for Mirex, which means we got a problem, right? All right, so that was our hypothesis test. We did a confidence interval and hypothesis test. The only other thing that we would need to do when we're dealing with just one sample is choosing a sample size. So what if we go back to that that one farm that had the outliers, really high contamination levels? Now we want to create a confidence interval to figure out what we believe the levels are for that farm. But it's so we're going to do 95% confidence level, and we want our margin of error to be within 1% parts per million. Now that's less smaller margin of error or a larger margin of error, so less precision than when we did our last sample. But because we're only talking about one farm, we don't want to spend that much resources on just one farm. So this is going to be more of a rough estimate, but it's only centered on this one farm to give us that margin of error, that confidence interval. So our let's say that our standard deviation is exactly the same. So we're assuming that the standard deviation is exactly the same. Now on this one, we would probably want to do a pilot sample or do a small sample to figure out if the standard deviation is much larger for this place. In the book, we'll talk about doing that as well. So a pilot is just a small scale, more of an inexpensive scaled down version of what we're trying to do. We use them to either test to see if our methods for gathering the data are biased or having issues in the wording or something like that, or any other problems that come up before we do the large scale expensive thing. So it's kind of like in Mythbusters, they always do a small scale version first before they do all the big production things to figure out what you can find out. I don't know why I put that there. All right, so to find the margin of error, we want the margin of error to be 1%. The t-star is going to be our critical value. That comes from our technology, but the problem is that it's tied to the sample size, and that's what we're trying to find is the sample size. So we can't find that yet. We'll fix it in a second. We're assuming that the standard deviation from this sample is the same as the old one from the big one. In this case, we probably have a larger standard deviation because the values are higher and there's probably more variation between those two, but that's okay. We don't have that data, so we're just going to use the old one. And then we're also dividing by the square root of n, just as we did before. Now, on this, if you notice, there are two variables that are dependent on the sample size, and we cannot solve for two variables at the same time. So what we do is we take a conservative estimate by using the critical value. So we don't know which family of values or what critical value we're going to use. So the best case scenario, if we had an infinite sample size, would be the smallest margin of error would be given by using a 1.96, which is using the normal model. So that's how we're going to use the most conservative. Then we're going to update it with a better, with a closer estimate for our sample size. So we're going to assume that it was normally distributed, which of course it's not. It's going to be definitely going to be more than that, but we're going to use 1.96 just to get us started. So I'm going to replace that with 1.96, which came from the normal model, not the t-distribution. So best case scenario, normal model here. So that's our conservative estimate. All right, so margin of error was plugged in there. We've got that value plugged in that. Okay, so all we have to do now to solve is to divide both sides by 1.96, and then we can switch those two in the order, then we square it. So I'm going to go ahead and do that over here just so you can see the math. So I'm going to do 0.01 divided by 1.96, and then I'm going to take 0.0495. I'm going to divide that. I guess I'll show it this way so you can see what I'm actually putting in. I'm going to divide that by the previous answer. So that would be second ANS. I'm kind of doing all this in my head, but it works, and that's going to be what in the square root of n is equal to. So to find the actual value of n, I just simply have to square it when I'm done. And that's going to give me an estimate of about 94. So if we have best case scenario, which would be a normal model, which we know we can't use because Gosset discovered that with his small samples of 4, when we do averages of small samples especially, it's going to be off, right? He had 3 times the false positives that he should have when he was sampling the 4 alcoholic beverages. So that gives us that value, so approximately 95. Yeah, so we can't have 0.13 of a person, so we always round up when we're doing our sample size. So based on this conservative estimate or initial estimate, we would need 95% or 95 people. So now that we know that we think it's about 95, we can now figure out which model we're using. So if we use degrees of freedom 94, that'll give us our critical value. So I'm going to go back into the technology. This is a bit of a process, isn't it? So second distribution, I'm going to do the inverse T, and I want 95% confidence, so I'll do 0.975. Degrees of freedom is going to be 94 because we had 95 people, we said. And that tells us that we should actually be using a critical value of 1.985 or 986 standard deviations for our confidence interval. So we update those values. So the critical value with Z star was 1.96, but for T star, it's going to be 1.986. So it's just going to be a slight change because it is such a large sample, but it doesn't make a difference. And when we do that, we get our critical value here of the T star, and redoing our math, we update it with a new value, which gives us 96.6, which we round up to 97. So I'm going to go ahead and run those numbers real quick for you. So everything stayed the same except the initial part. Okay, so we're going to do 0.01, and I'll do it this way so you can see. Divide by our new critical value of 1.986. Yeah, 986. Okay, then I'm going to take that and take my standard deviation divided by that value. So 0.0495 divided by the previous answer. So second ANS. Okay, and that's going to be just like here, the square root of n is going to be that value. So I got to square it, and that'll give me my new estimate. And again, we can't have 0.6 of a person, so we round up to the nearest whole number, which is 97 people. So what sample size would we need in order to get a margin of error of 1% parts per million for this other one? Well, we did our first initial using the normal model, which gave us 95. Then we plugged in with 94 degrees of freedom what the new critical value would be, reran our math, which now gives us 97. So a bit of an involved process here, but it's totally doable. If you think about it in the big picture, it should make sense. So those are all 3 of the different things that we would want to do when we have one sample of means. So whether that is initially getting a confidence interval, and then testing hypothesis, which is a little bit more advanced, and then lastly, choosing a sample size for a certain specific margin of error and level of confidence, so confidence and precision that we want for our sample. So that is pretty much it. I will we'll either post another day for a review tomorrow, or we're just going to move on to the next chapter. So I haven't made that decision yet, but I got to get off and making dinner for my parents. So I will talk to you guys. I'll see you tomorrow. I'll post a video for you guys tomorrow. We'll figure out what we're going to do. Make sure you guys are watching the videos. I am going to be, because I'm noticing that when we aren't giving out grades, we kind of have a drop off in the viewership, and I can see on YouTube just how much the videos are being watched or are not being watched. So I'm probably going to be changing some policy going forward where I have you guys turn in the assignments. They won't be for a grade, but I'm going to turn them in. That way, if you're not doing the assignments, I can give a nice friendly call home just to update your parents and let them know what you guys are or are not doing and turning in, because apparently you guys are not necessarily the most responsible, and if you tell someone that they already have a grade and they don't have to do any work and it's not going to impact the grade, they won't do anything. So we'll talk more about that later. I'll put it in a separate video, just what's going to be changing there. But to the few people who actually watch this video, you'll have a heads up for what's going to come up next. So I'll talk to you guys later. See ya.